So as we are making our way to finally solving that head check problem, let me just also say that one good thing about writing expectations and sum in this way as just one character that says expectation over such and such space or sum of those things is that you could do interesting calculations with it. An expectation is a very well-behaved operation, sort of like a sum, in that it has a property called linearity. So linearity means that if you multiply your expectation by a number, so if you multiply your random variable by a number, the expectation of that new random variable, your original one multiplied by some number a, will be number a multiplied by the expectation of the original. And also, if you take your original random variable x and add to it some number b, then the expectation of that will be expectation of your original number x, random variable x plus b. So in general, you could take your random variable and you could multiply it by something, by a constant, and you could add a constant. And once you take an expectation, rather than having to recalculate everything for that new random variable, you just take a outside the parentheses and get you and b and get a times expectation of x plus b. That's exactly the same thing that you could do with a sum, and here is the proof. And moreover, if you have two random variables, then expectation of their sum is the sum of their expectations. So we are going to use that. So now let's get back to solving the head check problem. So just to remind you, the problem was like this. N men left their hats, very much similar looking hats, at the door when they came to an event. They were rushing out. Each of them grabbed a random hat. They all look very similar. Hard to tell which one is which. So on average, how many men would have picked their own hat if this is what they were doing? So let's introduce a random variable for every man and indicate a random variable which will be 1 if the man number, so x of I will be 1 if man number I picked his own hat, and 0 otherwise. And the quantity we want to estimate is the expectation of the sum of x1 plus x2 and so on up to xn, which means we want to know on average how many of those xi's were 1. So now, for one man trying to randomly in a hurry pick a hat out of n hats, the probability of him picking his own hat would be 1 over n. So probability of each of those variables separately would be 1 over n. Now we could actually calculate the expectation. So for each xi, expectation of xi will be 1, because it's an indicator random variable, times the probability that indeed this variable came up 1, which is 1 over n. Finally, we can use that wonderful property, linearity of expectation, and say expectation of the sum of those variables is equal to the sum of the expectations. So what the expectation of one of those variables is 1 over n. That the chance that a man presented with an identical hat manages to pick his own. If we sum it up, it will be 1 over n plus 1 over n times. We get n times 1 over n, we get 1. So no matter how many men they were leaving their hats at the door, on average, just one man will go home with his own hat.